Welcome back, everybody. We are going to talk about determinants and inverse matrices today. If you hear the little ticky-tick walking around, that's just my dogs begging for food. So don't worry about them too much. They're super cute. They look even cuter than their feet sound, I promise. But we're going to talk about determinants and inverses of matrices today. So you're going to learn how to find the inverse of a matrix. This is the big thing. But we have to take a slight detour and talk about determinants. We are going to have 2 more lessons about determinants after this one. But you're going to learn most of what you need to know about them right here. So don't forget what I tell you. All right? Cool. So let's go do some learning. All right. Before we can actually do anything, you need to learn the words I'm going to say at you. So we need to talk about an inverse first. So an inverse is just something that undoes something else. Like if you multiply something by a half, you can undo that by multiplying by 2, right? So if you have like 2x times a half, that's x. And then if you times 2, you're back at 2x, which is where you started. So the times 2 undoes the times a half. You can think about multiplication and division as inverses. You can think about adding and subtracting as inverses. So there is a way we can find an inverse matrix. What that means is if I have a matrix and I multiply another matrix to it, I'm going to get, let's call it a green matrix. For matrices, there exists sometimes, not always, another matrix, a purple one, that if I use the purple one on this green one, it will take me back to the original red one, right? So we would say that the purple one is the inverse of the blue one. Right? The blue one changes red to green. The purple changes green back to red. So it undid what this blue one did. So the purple and the blue one are inverses of each other. Cool? Not every single matrix in the universe has an inverse. Like if we multiply by... Actually, let me back up. Let me give you a better example. If we we'll go with what I was thinking. If I have x and I multiply it by 2, I get 2x. And then if I multiply the answer of this by a half, it takes me back to regular x, correct? But not all multiplication has inverses. If I take x and I multiply it to 0, I get 0. And then if I take 0 and multiply it to anything else, I don't get x back. I get 0 again. So that you've seen things that don't have inverses before, but you've probably never thought about it that way. So there are matrices that undo matrix multiplication, but not every single matrix can be undone. There are some where it's impossible to undo them. Okay, so that's what we're going to learn to do today. And then you also need to be able to get a determinant. And for the life of me, I cannot explain to you what a determinant is. And part of it is because even though I have a master's degree in math, which means I'm okay at math, I'm going to be straight with you. I'm not 100% sure what a determinant represents. Okay. Let me just read you the definition that you'll find in most textbooks, and then we'll talk about, you'll see why it doesn't make sense to you, right? So in linear algebra, so this is from a linear algebra textbook, the determinant is a scalar value that can be computed from the elements of a square matrix and which encodes certain properties of the linear transformation described by the matrix. I'm sure that's complete just Chinese, Mandarin to you. The idea of a determinant is a really, really abstract one. It's not something where I can give you a clear example of what that does, because you don't really understand the idea of linear transformations being applied to vector spaces, and like the scalar probably means almost nothing to you. Scalar just means a number, but that probably doesn't narrow it down. You're thinking all this stuff is numbers. What's different about that? So me trying to explain what a determinant is to you is nearly impossible because you're not far enough in your math career. This is like Tony Hawk trying to teach a 900 to a kid that can't kickflip, right? It's not that the kid will never be able to do a 900 or kickflip. It's that there's just certain prerequisites of understanding that you have to be able to digest what this paragraph means, right? So I'm going to teach you how to find it. We can find these, right? We can understand what a 900 is in skateboarding without being able to do it, right? So I'm going to teach you how to do it, but not understand what it is, okay? So our goal is find matrices that undo other matrices, and we're going to use this mysterious determinant thingy with a bunch of words we don't understand to do it, okay? Now that you're having a mild panic attack, let me go fix that problem for you. All right, so let's talk about how do I calculate a determinant, and this is specific to 2x2 matrices. First of all, determinants only exist for square matrices. That's 1x1s, which is just a number. 2x2s, 3x3s, 4x4s, anything that's got an equal number of rows to columns. Okay. We are going to focus on 2x2s. Later, we will learn 3x3s as well. After that, it gets too complicated for us to want to do it. So, given a matrix A, so let's pretend you have a matrix, its name is A, and here's that matrix. It's got a 1 right, or an A right there, a B right there, a C right there, and a D right there. The determinant of this 2x2 matrix, and that's indicated by these double bars next to the, or around the matrix name, is equal to 1 over A times D minus B times C. Okay, so this is easy, right? We can take two numbers and multiply them, and take two other numbers and multiply them, and then subtract them and put them in a fraction. That's all you have to do. Okay. Ooh, look, see, you guys went from like this to this. Wait, hang on. It's been a long day, you guys. My drawing skills are not... Right? You went from panic mode to, hey, this is easy peasy mode, right? So let's go do an example. So here's a random matrix I made up, and I just made sure that it's going to work, right? And you're going to say, what do you mean make sure it works? We'll talk about ones that don't work in a sec. So I want to know, what is the determinant of this 2x2 matrix? So this is A, and we want to find the determinant of A. And we have that formula. It's 1 over A times D minus B times C. So A, B, C, and D just refer to the positions of these numbers. So this is A, this is B, this is C, and this is D. So we just plug these numbers into this formula, and then we're done. So the determinant of A is equal to 1 over A is 1 times D is negative 2 minus B is 5 and C is 3. Then we just simplify this. So 1 over 2 times negative 1, or sorry, 1 times negative 2 is negative 2, minus 5 times 3 is 15. Negative 2 minus 15, that's negative 17. So the determinant of A is 1 over negative 17. So let's maybe go unpack some of that definition, just so you guys are learning, right? So when they say the determinant in linear algebra is a scalar value, this is what they mean. Scalar means a single number, right? We took this weird collection of numbers and turned it into one number. And somehow this number has encoded, right? It's captured certain properties that we're not going to worry about of whatever linear transformations are. So this number tells us some information about what this thing does. But again, it's kind of hard to explain to you like what that means. But basically, a determinant takes a matrix and turns it into a number that tells you something someday. There you go. So there's our determinant. Now we are ready for finding the inverse. This is also pretty straightforward, even if we're not 100% sure what this even means. Just because we don't understand something doesn't mean we can't do it, right? Like a 2-year-old could accidentally hurt themselves with a knife. They don't understand how they harm themselves, but they could do it, right? So we can still do these things without really understanding what we're doing. So given a 2x2 matrix A, and this is just the same generic like placeholder matrix. So we have a matrix A. The inverse of A, and the way we denote inverses in math is a little -1 exponent. I personally hate this notation, but we're stuck with it. Equals 1 over AD minus BC. This thing, this little chunk here, this is the determinant of A. Cool? So this is the determinant. So it's the determinant times. Now this little chunk here is just our original matrix with some rearranging and some sign flipping. So A and D have switched spots. So these diagonals here, we swap their spots. Then B and C are just negative now. And then that's it. Cool? Easy, easy, they say, Mr. Barton. All right, so let's go and look at an example. All right, so this is the exact same matrix that we have already found the determinant of, and I'm just doing this to kind of speed things along. So here's A. The determinant of A, we've already figured out that that's 1 over -17. If you forgot that, go look back 2 slides ago. Okay. The inverse of A is equal to the determinant of A times D negative B negative C A. Okay, so we already have this chunk right here. We have our determinant. It's -1 over 17. Now we just have to rearrange this and then slap this thing on it. So we're going to switch the position of A and D. So that's going to be -2 and 1. And then we have to change the signs of B and C. So this will be -5 and -3. All right. So now you could write your inverse like this if you don't like having fractions. But when we have a scalar, meaning just a number, and this is being multiplied to the matrix, those rules that we learned about matrix multiplication in the last video don't really apply to scalars. You are supposed to take this number here and distribute it to each element. So we'll do that because that's how your homework's going to look. So negative times negative is positive. And when we multiply these numbers to a fraction, we're just multiplying these numbers to the top. So basically these numbers go on top and it's over -17. So -2 over -17, we'll just cancel the negatives, and that's 2 over 17. -5 over -15, again we cancel the negatives, and we get 5 over 17. -3 over -17, again our negatives cancel, and then 1 over -17. So this matrix, if I multiply A to something, if I multiply this matrix to whatever that answer is, it'll give me back the original matrix. It'll undo this A right here. Cool? Nah, not cool, Mr. Barton. That's super lame. Why would I ever want to know this? Fun fact. Let's take a small aside. I'm gonna humble brag at you guys real quick. Let's define humble brag. Okay. Humble bragging is where you say you've done something that sounds super impressive just to flex on people, but you say it really nonchalantly. It's like, oh, when I was vacationing in Panama last year, I saw an elephant. It's like, okay, bro, not all of us get to vacation in Panama. Chill, right? So when I was doing my master's degree, I had to take that mysterious class, linear algebra, which is basically the math of matrices, right? There's a whole math class just for matrices. It's more than one unit in real life. When I was doing my master's degree, we had to do projects to like prove that we could use the math we were learning for something useful. So one of the projects that we could do was facial recognition. So what you do is you take a picture. So let's say here's a picture of me, right? How do I make this as handsome as possible? We'll put a little bow tie on me, right? So you can take this thing, and then of course we know that digital pictures are made of pixels, so they're little tiny colored dots. You can take all those pixels and put them in a matrix, and it's not a little matrix. This is whatever the resolution of this thing is. So probably like a regular phone screen or like older computer screens are 10,080 pixels tall and 1,980 pixels wide. This is like HD resolution. Not 4K or anything super bougie, but it's pretty big. It's nice. It's all right, you know? So you take every single pixel. So you take 1,080 things and 1,980 things, and you turn that into a matrix that's this big. This is the order of the matrix. Then you hit it with some math operations, and then you hit it with some inverses, and then it tells you that you're a person, right? It goes, this one here, that's also Barton, but from the side, right? So your Snapchat filters, all the things that make you guys look like goofy frogs and stuff online, the math that Snapchat does is this math to make you look funny. So, I mean, it has real practical applications, but to be able to use this to make a Snapchat filter requires literally like a master's degree in math, more or less. So it's pretty difficult, but I bet the person who made Snapchat filters is pretty freaking rich right now. So, okay. So that concludes 2x2 matrices. We did inverses and we did determinants. Those things you need to memorize for the rest of your life. Now we're going to do one example of finding the inverse of a 3x3 matrix. That includes a lot of things. It includes putting an augmented identity matrix on this thing, and the identity matrix is this. It's all the diagonals are 1 and everything else is zeros. And then you have to do this thing called Gaussian elimination to turn it into reduced row echelon form. So right now I'm just super flexing on you guys, throwing out every weird linear algebra word I know. But when I show you the example, you're gonna be like, oh, I can do that. So let's go look at the example. I even numbered some steps for you guys. So we're gonna find the inverse of this matrix right here, this one. But unfortunately, I'm not going to be able to fit it on this screen. So we got to go to the next screen. So step 1 is type 3x3 matrix inverse calculator into Google. Step 2 is click on the first one that shows up that says matrix inverse calculator. Step 3, you need to tell it you're going to put in a 3x3 matrix. So you click the little 3x3 button. And then this thing will show up with little blanks here. Then you type your matrix in. Okay, cool, wonderful. And then you wait for a second, and then ta-da, there's the inverse. So to be honest with you, finding the inverse of a 3x3 matrix is a ton of work. If you try and do it by hand, it takes up, I think, like a minimum of an entire piece of paper. So this is not something you're going to learn how to do in my class by hand. When you go to college and you take linear algebra, they'll show you how to do it by hand. You actually do all those big math words that I said. You see this? Gauss-Jordan. That's Gauss-Jordan elimination. Diagonalization, which is related to that row echelon form. Eigenvalues are a thing. Eigenvectors are kind of fun. But I digress. On your homework, they ask you to find the inverse of 3x3 matrices. Okay. When they do that, go to this website, symbolab.com. Just Google 3x3 matrix inverse calculator. Click on symbolab.com. Click 3x3. Type in your matrix. Click go. And then it'll spit out the answer. And then you're done. Typically, what I do is show you how to do this on the Casio calculators, but I don't have a Casio calculator, and even if I did, I don't really have a way to record the screen of a Casio calculator right now. So you're gonna just use this website. If you find another website you like more, go ahead and use that. But to do all those problems, you just Google it and make a computer do it for you. Cool. All right. Let's go back and talk about one thing. I think I may have almost skipped something, but thankfully I haven't hit stop recording yet. Let's talk about this determinant because I said there are things that won't work. Let me make one that won't work. Watch this. Let's say our matrix equals 2, -3, 4, 6. Wait, is that what I want? -4. Okay. We're going to find the determinant of this thing. So one more time, the determinant of A is 1 over AD minus BC. So this is 1 over A times D minus -3 times -4. I bet you can kind of see what it is already, right? You can see the problem. So this is 1 over 12 minus -3 times -4 is 12. So this is 1 over 0. This is the biggest no-no in all of mathematics. If you divide by 0, the universe ends, you create a black hole, 1 equals 2, your mom equals a dog, right? Oh no, you just turned your mom into a dog with this. How dare you, right? So if you get a determinant that is 1 over 0, that means that it is undefined and you cannot find an inverse. It's impossible because you can't multiply something by something that doesn't exist. And I don't mean it doesn't exist like it's an imaginary number. I mean it just straight up doesn't exist. Like it's not a thing. There's no math textbook in existence that'll tell you how to do it. So if you ever get a determinant of 1 over 0, you're done. And if they ask you what is the inverse, so what's the inverse of A? And you calculate your determinant and you get 1 over 0, you just stop the problem and you write undefined instead. Okie dokie? Cool. All right, now that you have no idea what you're doing, you're gonna go try and do that. So I will be in WebEx as always to hold your hand and, you know, spoon feed it to you. I'll even make the little airplane noises as we fly the example problem into your mouth. Well, here comes the airplane. Wow. So if you need any airplane noises or you need a hug, maybe some words of encouragement, I'll be in WebEx. You know where to find me.